Welcome to the Chemistry, Biology, and Math Revision Hub. This is the Pearson Edexcel International A-Level Chemistry Unit 3 for January 2022. This paper is 50 marks, as you can see here. So I will go straight to the first question. Question 1 says, this question is about ammonium chloride, a soluble ionic compound. An aqueous solution of ammonium chloride contains both ammonium ions, so we can see here, and chloride ions. The first question asks you, state what would be seen on the addition of acidified silver nitrate. Acidified silver nitrate can be nitric acid mixed with silver nitrate. So solution to an aqueous solution of ammonium chloride. So if you add nitric acid and silver nitrate to this, we would expect that the silver ions from the silver nitrate will react with the chloride ions from the ammonium chloride to produce silver chloride. So silver chloride is a solid, so that is why this is going to be the precipitate. And then this is going to be aqueous soluble, and that is going to be aqueous. So that is the white precipitate we're going to observe because of silver chloride formation. So this, a white precipitate forms, is correct. The next part says, describe a test to confirm presence of ammonium ions in a solution of ammonium chloride. Include the result of a positive test. Now we know that if there is ammonium ion in a specific solution, what we need to do is you need to add sodium hydroxide. When you add sodium hydroxide, a reaction will occur inside that reaction vessel producing ammonia. However, this ammonia is going to be dissolved. Or it will not be coming off as a gas easily. So what we do is we need to warm. When we warm, this increases the temperature and the gas bubbles, or the gas is actually going to be evacuated out of the solution. So when we test that gas with damp red litmus paper, we're going to see that damp litmus paper turn to blue color. And that's how we can confirm that the gas that came off was ammonia, and therefore it must have come from an ammonium cation. The next question says, a student investigated the enthalpy change when dissolving ammonium chloride in excess water. So the water is excess, it means all the ammonium chloride solid will be dissolved. The procedure: accurately weigh 7.17 grams of ammonium chloride into a glass beaker. Fill a 50 centimeter cube measuring cylinder with the ionized water. Then measure the temperature change of the water using a thermometer. One thing we need to know here is because this is dissolution, this is going to be endothermic. So heat has to be brought in from the surrounding into the system. And therefore, we would expect that the temperature is basically, since it's coming into the system, the temperature could initially become colder within the liquid until the reaction is completed, basically, because the heat is going to be taken out of the solution to be able to initiate the reaction or to allow the reaction to go on further. So the solution is basically going to cool. So they say pour the water from the measuring cylinder into the beaker, and at the same time start a stopwatch. Stir the solution in the beaker using a thermometer, and then record the temperature at 15 seconds, 30 seconds, and then at 30-second intervals while continuing to stir the solution. They say the data from the experiment is shown on the graph. I'm going to move on to the next page. So again, this is my graph. Please, you don't have to look at the graph I drew. The blue color and the green color, this is my data. However, you can see the points were already plotted for us, like that point, that point, that point, that point, that, and that were already plotted. Everything else, I drew it in there because it was required for me to be able to answer the question appropriately. So here the first question says, give 2 reasons why the student stirred the solution in step 3 and in step 4. The reason for stirring, again, I want to take you back. Let's see step 3 and step 4. In step 3, they say pour the water from the measuring cylinder into the beaker, and at the same time, start a stopwatch. Stir the solution in the beaker using a thermometer. So here, we want to make sure in step 3, so they pour it into the stopwatch. Remember, they already have a solid in there. So this is to make sure that the dissolution of the solid occurs. And then step 4, they say record the temperature at 15:30, and then after 30-second intervals while continuing to stir. The second stirring is to ensure that there is uniformity or uniform distribution of temperature or heat within the solution. The first, in step 3, again, let me erase this. In step 3 is to ensure the solid dissolves, and then in step 4 is to ensure that heat is uniformly distributed throughout the reacting vessel. The next part says use the graph to determine the maximum temperature change, delta T. In this experiment, you must show your working on the graph. So my working is in blue, as you can see on the graph. Since this was the initial temperature, the one you can see here, so after adding, remember they added the ammonium chloride here, and then the temperature began to drop. You can see it went here, it came here, the temperature dropped. Let me use another highlight. So the temperature dropped here, it came there, and then slowly afterwards it began to increase. There is a reason as to why this temperature was dropping. It means the reaction was still going on. But when the temperature begins to increase, it means the reaction has stopped, and therefore maybe the heat is coming from the surrounding into the container or into the reacting vessel, trying to warm up the solution. So there is equilibration between the surrounding, which is the air or the environment within the lab, and the solution. So heat is coming in, so there is an increase in temperature. But this initial decrease was due to the reaction taking up the heat from the solution in order to be facilitated. So what you have to do is you draw a straight line through the first initial point, and then you draw another straight line through the other initial points. We call this the line of best fit, and where these two lines of best fit meet, that is the point at which the reaction was stopped. So basically, we know the point where the reaction began, this point here, the temperature was 19.7, and the point at which the reaction was completed must have been 10.8 degrees Celsius. So to be able to calculate the temperature change, it's going to be 19.7, which is the maximum at the highest temperature, minus 10.8, giving us a temperature change of 8.9 degrees Celsius. So that is it. I will go to the next page. They say another student carried out the experiment using a polystyrene cup in place of a beaker. So previously they used a beaker. If you use a beaker, we expect that the heat from the surrounding is going to come in a lot. However, if somebody uses a polystyrene cup, it means the polystyrene cup provides insulation, so the heat coming in is not going to be great. Therefore, the other time when the temperature began to increase with a polystyrene cup, the increase is not going to be as much. So the question here they're asking is, explain how the student's graph would be different. You may annotate the graph as part of your answer. Like I said here, remember the minimum temperature here is going to be lower. The reason for this is since we are using the second part of the plotted points to draw a line of best fit. Again, let me take you back to the graph. So if you use the polystyrene cup, it means the temperature is not going to increase as it would increase if you use the glass beaker, because the polystyrene cup provides insulation. So I would expect this temperature to be a little bit lower than that all the way. It's gonna increase uniformly like we saw that, but it's not gonna be exactly the same at the same time. So it's always gonna be lower at the same time. However, since we are drawing a straight line through this point, or line of best fit through this point, in order to predict the point at which the reaction must have stopped, using a polystyrene cup, our temperature will be about 10.2 based on my data. Another student could have used a lower value. So for my case, it's 10.2, which is going to be lower than the 10.8. And I hope you can see that. So I'm going to take you back to the point I was trying to pass along. The minimum temperature here is going to be lower, and according to mine, example is 10.2. Here again, the temperature would increase at a slower rate, and then less heat would enter the solution from the surrounding. My explanation is on the graph, and the reason for this is the polystyrene cup provides insulation around the solution, and therefore preventing heat to come in as much. Therefore, there will be a slower increase in the temperature of the solution after the reaction is done. So let's continue to the next part. It says the experimental results of another student were used in the equation shown to calculate the enthalpy change, delta H, for the dissolution of 1 mole of ammonium chloride in excess water. They ask us, state 2 assumptions made in this calculation. Whenever we use this kind of calculation, since they've said this is going to be the specific capacity, that, and that is going to be the mass, we can see that they've assumed that density is 1 gram per centimeter cubed since volume is equal to mass. And also we can see that the mass of the solid that has been put is ignored. If you have used 50 centimeters cubed of water and you have added a solid, yet you assume that the mass is 50 grams, it means you have not considered the mass of the solid that was added. And lastly, they have assumed that the specific capacity of the water is equal to the specific capacity of this solution. Let us continue to the next page. Roman 2, the total percentage uncertainty in this experiment is 2.6%. They say show that the enthalpy change, which is 14.5 kilojoules per mole, is consistent with the data booklet value of 14.8 kilojoules per mole. So here the uncertainty in the experiment is going to be 2.6 over 100 times the value we have measured, which is 14.5 kilojoules per mole. When we do that multiplication, we get a 0.377 kilojoule per mole as the uncertainty. So to be able to find the correct value should be the 14.5 kilojoules per mole plus the 0.377, giving us 14.877 kilojoules per mole. And since this value here is almost approximated to the data booklet value, you can see we can assume that the enthalpy change is actually consistent. So I said here, since the data booklet value, that is consistent, and that is approximately the same as this. So basically this is the data booklet value. While this is approximated to that, we can confirm that the change is consistent. This brings us to the end of question 1. I will move on to question 2. Question 2 says, this question is about two organic compounds, X and Y. Both are liquids which contain carbon, hydrogen, and oxygen only. So basically they say the mass of hydrogen and of carbon present in 1.33 grams of X were determined by passing its combustion products through the apparatus. So you can see this is where they put the sample X. It was heated in presence of oxygen, and then the products went through here. Remember, for any combustion, complete combustion of this organic compound, we're going to produce carbon dioxide and water. So here we see the water is going to be absorbed by the silica gel, and then here we can see the carbon dioxide is going to be absorbed by soda lime. And then the excess oxygen is going to be passed out. The first question says, state the measurements that should be made. Measurements, we need to measure the masses of these two tubes before the experiment, that is, after putting the silica gel and the soda lime. And then we need to measure their masses at the end of the experiment, that is, after they have absorbed carbon dioxide as well as water. To do this, it helps us determine the mass of water absorbed as well as the mass of carbon dioxide that has been absorbed, so that we can be able to predict the masses and therefore use those masses to find the mass of hydrogen and the mass of carbon in the carbon dioxide. So the next question says, give 2 reasons why pure oxygen and not air should be used. Now you should know, in air there is oxygen, there is carbon dioxide, there is water vapor, and so many things. So if we use air, it's going to contribute to the carbon dioxide, the mass of carbon dioxide, which we do not want to occur. And also water contains, air contains water vapor, so this is going to contribute to the mass of water. So to exclude the contamination from the water as well as the carbon dioxide, pure oxygen has to be used to exclude CO2 from air and allow complete combustion, as well as excluding the water vapor from the air. I'll continue to the next page. The experiment shows that 1.33 grams of X contains 0.14 grams of hydrogen and 0.63 grams of carbon. Calculate the empirical formula of X using this data. You must show your working. So here, since we know the mass of hydrogen and the mass of carbon in basically the organic compound, we're given compound X, we can use the mass of this and that, get that sum, and then subtract it from the original X to be able to find the mass of oxygen. So mass of oxygen will be the mass of X minus the sum of the mass of hydrogen as well as the carbon to give us 0.56. After finding that mass, we can use we can basically find the number of moles of each. So moles of carbon will be the mass of carbon divided by the atomic mass of carbon, giving us that. Moles of hydrogen will be the mass of hydrogen divided by molar mass of hydrogen, giving us that. And moles of oxygen will be the mass of oxygen divided by the molar mass, or atomic mass, giving us that. Then we can divide through to find the whole number ratio, Here we divide through using the smallest number of moles, which is going to be that divide by that, that divide by that, and that divide by that, giving us a 1.5, a 4, and a 1. Now, if you get a mole ratio which is in decimals, sometimes you have to multiply through to find a whole number ratio. So 1.5, we have to find the smallest whole number ratio, so we're going to multiply by 2 to create a 3. We have to do the same thing to all. So if you multiply this by 2 to get you 3, you should multiply this by 2 to give you 8, and that by 2 to give you 2, giving us this as the final empirical formula of X. The next question says, when phosphorus pentachloride is added to X, steamy, here let me underline this, steamy white fumes form. So as seen, state what can be deduced about X from this observation. Steamy white fumes are going to be, of course, HCl gas as it comes off. Remember the reaction that will occur. Anything that contains an alcohol, when it reacts with PCl5, we're going to produce RCl plus POCl3 plus HCl. This is responsible for the steamy white fumes, and therefore it tells us there is an OH group present in X. So this could be OH alcohol, or it could be OH carboxylic acid. So I just confirmed that X has an OH group. Let's continue. So they say compound X is converted into compound Y when refluxed with excess sodium dichromate in sulfuric acid. Now this is telling you about oxidation. If X can be oxidized, we know X has an OH group, but it can be oxidized. So it means X could be, because it can be oxidized, it could be an aldehyde or it could be an alcohol. This is just telling us it could be an aldehyde or it could be an alcohol. However, if it's an alcohol, it is going to be only primary or secondary alcohol. It cannot be a tertiary alcohol, because tertiary alcohols cannot be further oxidized. So they cannot be oxidized basically to anything else. So here we can confirm either aldehyde, because it's oxidizable, or it could be alcohol, which is primary or secondary. So remember, they've told us why. So they say Y is a liquid that is soluble in the reaction mixture, meaning it can form intermolecular hydrogen bonds in a solution and aqueous solution, so basically with water. They ask you, draw a level diagram of the apparatus that could be used to separate Y from the reaction mixture. Since we are trying to separate Y from the reaction mixture, we need to do a distillation, and therefore we can see here the distillation setup should be, there is a boiling tube down here, and then you heat it. We have a condenser connected to it, and then a collector this side. You can use a side arm, and then the thermometer has to be positioned at this point. Please remember, the bulb of the thermometer should be positioned at the point where the contents are going to enter into the condenser. And then the condenser should be positioned that water comes in at the bottom area, the slanted area, and then water leaves out at the upper part of the condenser. So this is usually a 3-mark question, and as you can see, it's 3 marks. I will move on to the next part of the question. Here they say the infrared spectrum of Y is shown. So this is the infrared spectrum of Y. We have transmittance and wave number on the x-axis, transmittance on the y-axis. They've also given us a table of some infrared absorption data. You can see all the bonds as well as their corresponding wave numbers. So the first question here asks, explain how this spectrum shows that Y contains a carboxylic acid functional group, quoting data from the table. A carboxylic acid functional group is going to have this. Let me actually make it the O and minus H. So it means it will have this bond as well as that. So we have to look if there is anywhere we will see a peak from our infrared spectrum that corresponds to those kinds of bonds. So we are looking for this kind of bond here, and we are looking for OH carboxylic acid. Is there a peak around this area and the peak in this region? Of course, when you look at this, we see there is a broader peak around this point, which confirms presence of basically oxygen, hydrogen in carboxylic acids. And there is a peak here, this peak here, confirming a carbon-oxygen double bond for, it could be aldehyde, ketone, or carboxylic acid, but in this case we can confirm it's for carboxylic acid. So here I said there is a broad peak at 3 to 20 per centimeter, indicating OH carboxylic acid. And then there is a peak at 1720 per centimeter, which indicates carbon-oxygen double bond. This could be carboxylic acid aldehyde, or it could be ketone, but at least it's there. This confirms that that could be a carboxylic acid. Next, they say the mass spectrum of Y is shown. So we have here the mass spectrum, and they ask, show that the mass spectrum is consistent with Y having the molecular formula that. When we add this up, we get 88. Yet when you look here, the last peak or the molecular ion peak is at 88. So I say the molecular ion peak is at mass to charge 88. Also, the relative molecular mass of this is 88 gram per mole. Therefore, it is going to be consistent. The next part they ask, suggest the structure of the ion causing the peak at 43. Now, from your table in the AS textbook, you remember there is that 43, and there is this CH3, CH2, CH2, that could be 43. However, since we have a carboxylic acid here, and then we basically had OH group in the X, and the Y should be a carboxylic acid, there is no way this is going to be 43. 43 is going to be due to this, that fragment, basically. So the mass to charge at 43 is going to be caused by this fragment, so this should be the right answer, and not that. It rolls out there. Let's continue to the next page. Compound X contains one type of functional group. Remember, we saw that compound X has OH, which could be alcohol or it could be basically OH carboxylic acid. But since they have told us it has one type of functional group, it means it can never be carboxylic acid, because the carboxylic acid would never have been oxidized. So that tells us it is definitely an alcohol. And if it's an alcohol, it's going to be either primary or secondary, not tertiary. So we can see that. Okay, then they say Y contains two different functional groups. If X contains one functional group while Y contains two functional groups, it means those functional groups, let me see, X transitioning to Y, oxidation occurred. If X had one functional group and we have established it was OH, and oxidation occurred, here we produce two different functional groups. It means the functional group present in here cannot be OH, because OH, if it was present, it would be oxidized. It means we must have produced maybe a ketone and a carboxylic acid. So it means X must have had a primary alcohol as well as a secondary alcohol. So here they ask, use the information in the question to deduce your answer. So here we can see X must be a diol, meaning it has a primary and secondary. So this is primary and that is secondary, meaning the primary was converted to the carboxylic acid, and then this one here was converted to the ketone in the oxidation reaction. Here they ask you compound Y. Compound Y, of course, is going to be a carboxylic acid on this side, and then a ketone on this side, because this ketone must have come from the secondary, while that must have come from the primary when they were oxidized. This brings us to the end of question 2. Question 3. A student used a precipitation titration to determine the value of X in the formula of a sample of hydrated barium chloride. So this is the hydrated barium chloride. The procedure is as below. Prepare a solution by dissolving 1.57 grams of barium chloride in the ionized water, making the solution up to the mark in a 250 volumetric flask, and then mixing thoroughly. Number 2, use a pipette to transfer 10 centimeters cubed of barium chloride solution into a conical flask. Add excess sodium sulfate as solution and stir the mixture. Then fill a burette with 0.0324 mole per decimeter cubed of silver nitrate solution. Next, add 3 drops of potassium chromate. This is potassium chromate solution to the conical flask and titrate the contents while swirling with the silver nitrate solution. The end point is shown by the appearance of a permanent pale red precipitate. And 5, they say repeat step 2 and 4 until concordant results are obtained. During the titration, 2 precipitation reactions occur. So number 1, they say the silver ions react with chloride ions forming silver chloride. You can see this reaction here. And then the second reaction, they say once all the chloride ions have reacted, silver ions react with chromate ions to form a red precipitate of silver chromate. This is the reaction that will occur. Give the ionic equation for the reaction that occurs when sodium sulfate solution is added to the conical flask in step 2. Include the state symbols. Here what we have to know is, of course, when they added, there were barium 2+ ions and there were sulfate ions. So barium ions reacted with sulfate ions, producing a white precipitate, which is barium sulfate. as the solid, so it's a precipitate. The next part says, give a possible reason why it is necessary to add sodium sulfate solution. Justify your answer. So addition of sodium sulfate ensures that we remove the barium ions, because if they were present, the barium ions would react with the chromate to produce barium chromate. That this reaction would occur to produce barium chromate, which would interfere with our reaction. So to prevent this, you add sulfate in order to remove the barium 2+ ions, leaving the chromate alone in order for them to react with the silver in the next step of the reaction. So I will continue to the next page. So here they say suggest why the red precipitate of silver chromate only forms after all the chloride ions have been reacted. What we need to know is that the silver chloride is going to be less soluble than the silver chromate, and because of this, it ensures that basically the reaction is just going to occur only after the silver chlorides have been removed, because silver chloride will be less soluble than the silver chromate. So the next part says some data obtained in the experiment are shown below. So they gave us all the data, and they want us to complete the table and use the concordant results to calculate the mean titer. So how do you conclude? So basically we have to find the value here. That minus that gives us that, and then okay, we're gonna say this minus that will give us that, and that minus that gives us that. So basically the final burette reading minus the initial burette reading gives you the titer value, or the titer that was used in that experiment. So after getting this, that and that, we have to find out if they are concordant. Let's compare this and this. The difference between them is 0.1, so they are concordant. That and that, the difference between them is about 0.05. They are concordant. And then the difference between that and that is 0.05, meaning they are concordant. So all the three results are concordant, but this is far away from the rest. It is not concordant with any. So we can see that titer 2, titer 3, and 4, all these titers are concordant. And therefore, to find the mean titer, we will add up that plus that, divide by 3 to get a 15.85 centimeters cubed as the mean titer for this titration basically. Determine the value of X in the formula of the hydrated barium chloride, of course with XH2O. Use the information from the procedure and your mean titer in C Roman 1. You must show you're working. So the key thing to understanding here is the original salt was barium chloride, hydrated barium chloride. If you break it apart, you're going to produce barium chloride as well as water. However, so we were told to be able to find basically we are trying to find the value of X, we need to find the mass of that, and probably use it to find the mole ratio so that we can find the value of X. So what we begin with, we always begin with the information given. We are given the concentration of silver ions and the volume of silver ions, so we can begin from there. Because you remember we have the mean titer. The silver ions were in the burette, so if we have its concentration as well as the volume used, we can be able to predict the number of moles of silver ions and begin from there. So number of moles is concentration times volume. We know the concentration. And I divided the volume by 1,000 to convert it to decimeters cubed, and the final answer I get is 5.1354 times 10 power negative 4 mole. These are the moles of silver ions that were present. However, remember, let me try to show you how the whole experiment is. We have barium chloride. This barium chloride hydrated separates into barium chloride as well as that. Now consider this barium chloride as this barium chloride here. This barium chloride is going to dissociate, releasing barium ions as well as twice chloride. Remember, 1 mole of barium chloride contains 1 mole of barium 2+ and 2 moles of chloride minus. Now remember, each chloride is going to react with silver. Since we have 2 moles of chloride, we will need 2 moles of silver. So the ratio is going to be a 1-to-1, but it's going to be twice, giving us 2 moles of silver chloride, which is basically a solid. Let me erase that part there. It's going to be 2 moles of silver chloride as well. So if you work back, you can see 1 mole of barium chloride produces 2 moles of chloride, or 1 mole of barium chloride. The ratio of barium chloride to silver ions is going to be a 1-to-2. So 1-to-2. So since in barium chloride we have the barium ions, I can conclude that the ratio of barium ions to silver ions is going to be 1-to-2. therefore, since we know the number of moles of silver ions, we can use them with the mole ratio to predict the number of moles of barium, or to calculate basically the number of moles of barium ions. So this is my next step here. So I'm going to use the number of moles of silver ions to be able to calculate the number of moles of barium ions. So moles of barium ions, these are the ones that reacted, meaning in the 10 centimeters cube should be 1/2 times the moles of silver ions, giving me this. I hope this explanation, this one here, shows you why I used 1/2. It is because the ratio of barium to the silver is 1:2, since each barium chloride produced 1 barium but produced 2 chlorides which reacted with 2 silvers. So basically it's a 1:2. Now that I know the moles of barium ions in 10 centimeters cubed, remember this is the volume in the conical flask, I can use this to be able to work backward or to scale up to find the number of moles in 250. So the moles in 250 will equal to the moles in 10 times 25, giving us 6.41925 times 10 power negative 3. I avoid rounding off because I want to avoid carrying up the error to the next step. Now that we know the number of moles in the 250, these are the moles of the whole salt, the hydrated salt. So I want to use the moles of the hydrated salt and the mass of the hydrated salt given to find the molar mass of that hydrated salt. So this is going to be mass divided by the number of moles. I have both, and when I do divide, I get 244.58 gram per mole as the molar mass of the hydrated barium chloride. Now there is something, I know barium and I know chloride, so I can subtract the mass of these from the mass of the whole complex basically, or the whole compound. So since this is the mass of the whole compound minus the molar mass due to barium chloride, I remain with a 36.277, and this is solely due to water. So this is XH2O equal to that. Now since I know that water is 18, I'm going to divide that by 18 to give me this. Now, this is going to be the value of x, and since x should be a whole number value, I rounded it off to 2, and therefore we found the value of x in the hydrated barium chloride sample. This brings us to the end of question 3. Let us move on to question 4. Question 4. This question is about the preparation of anhydrous aluminium chloride, which reacts vigorously with water and must be stored in tightly sealed containers. A sample of anhydrous aluminium chloride was prepared by passing chlorine gas over hot aluminium foil using the apparatus shown. So we can see this is the reaction. Aluminium solid reacts with chlorine gas, giving us aluminium chloride, which is going to be a solid. In this setup, we can see there is potassium manganate 7 here, and then we can see this is concentrated hydrochloric acid. The two are reacting, and then anhydrous calcium chloride. So we see there is aluminium foil. So this anhydrous calcium chloride is basically a drying agent, so that whatever comes in does not have any water to prevent the vigorous reaction. So we see aluminium foil. This is going to be burnt, so the reaction takes place here. This is the combustion tube, and then there is a receiver. Here we see there is potassium hydroxide. We have an absorption tube, and then ceramic wool. Potassium hydroxide is to absorb any waste, basically. So let's see, they say procedure. Assemble the apparatus with about 5 grams of potassium manganate 7 in the pear-shaped flask, 10 centimeters cubed of concentrated hydrochloric acid in the top funnel, and a known mass of aluminium foil in the combustion tube. Step 2, carefully open the top of the funnel, allowing the acid to enter the pear-shaped flask, drop by drop. Wait for 20 seconds. Step 3, heat the aluminium foil until it brightly glows. Continue heating until the reaction is complete. So reaction will be complete when the glowing stops. Allow the apparatus to cool before closing the top of the funnel. Remove the receiver bottle quickly. Scrap the product into a sample tube and seal the lid. We are sealing the lid after basically scrapping out the sample. I will go to the question page. They say A, granules of anhydrous calcium chloride are held between 2 ceramic wool plugs in the combustion tube. Explain the purpose of the anhydrous calcium chloride. This is easy. Anhydrous calcium chloride will absorb water, any water present from the previous reaction before the contents come into contact with the aluminium foil has to be removed, because you remember water will react vigorously with aluminium chloride. So to remove the water, it's a drying agent. The next question says, give the reason why granules of anhydrous calcium chloride are used rather than powder. So granules are going to allow for the gas to go through because there are spaces in between the granules in comparison to the powder that is going to be packed tightly close. So this is basically to allow pathways for the gas to diffuse through faster in order to reach where it has to, where the reaction is going to take place basically. So here B says the reaction occurring in step 2 produces chlorine gas. Identify the main hazard related to chlorine gas, giving the best way to minimize the risk when using it. Chlorine gas is highly toxic. So when we're experimenting with it, you have to use a fume cupboard to prevent contaminating the lab environment or even you breathing in those fumes as you do the experiment. The next, give a reason why the concentrated hydrochloric acid is added drop by drop to the Piaget flask. Every time you see something added drop by drop, it's because you do not want the reaction to proceed very fast. So here, to ensure that chlorine is not produced too quickly. You do not want to produce a bigger volume of chlorine within a small space of the lab. So you add drop by drop to slow down the production of chlorine, since it's a toxic gas, and these fumes, if they come at a faster rate, they could contaminate the lab environment. So you want a steady flow of chlorine so that it can be suctioned out or sucked out in the fume cupboard properly. Let's continue. So this is the last page. Suggest why the heating of the aluminium in step 3 is delayed for 20 seconds after the initial production of chlorine. So this 20-second delay allows for air to be replaced basically. So air is going to be displaced. There is going to be some air in the apparatus. It has to be displaced before you begin the reaction because chlorine is going to be there. So that chlorine is displacing the air so that when you heat, it's only chlorine present in the tube, and therefore any reaction will be due to chlorine reacting with the aluminium foil. Practice says that how you would know the reaction is complete in step 3. Of course, the aluminium will stop glowing because you remember when you heat, it glows. So at the end, it will stop glowing, and then we can conclude that the reaction has come to an end. Lastly, suggest the purpose of the potassium hydroxide in the absorption tube. It has to absorb the unreacted gases. This is the waste gas, so gas that is not used, and this is chlorine in this case. Anhydrous potassium hydroxide absorbs it in order to prevent it from being released into the lab environment because it's highly toxic. So this brings us to the end of this paper. It was 50 marks, and I hope to see you in our next video. Please remember to subscribe to our channel, and thank you for being with us. Bye-bye.